Hi, my name is Dylan, and this is the presentation for my group's project, Diffraction Patterns of Red and Green Light. Before we get into our project, you need a little background on wavelength and diffraction. Wavelength is most easily explained in relation to the visible spectrum of light. There are many different wavelengths of light, and each one corresponds to a different color. For this project, we used red and green light, which have wavelengths of 700 and 550 nm, respectively. Now, diffraction is when a beam of light, or in our case the red and green lasers, spreads out after passing through a narrow space or along an edge. For our project, we used a device with two small openings that will create a pattern of light that corresponds to its wavelength. Now, the patterns of diffraction and the wavelength of the light making them are directly proportional. When wavelength increases, so does the magnitude of diffraction. When it decreases, so does the magnitude of diffraction. That's what this project aims to prove. The most important part of our project is perhaps the equations. Delta y equals lambda times L over d, where lambda is the wavelength, L is the distance from the viewing screen, and d is the distance between the slits of the apparatus. And delta y is the fringe spacing that we are calculating. So green light diffraction, we ran the green and the red light through the same apparatus with the same spacing between the slits, where the slit width was 0.04 millimeters and the slit separation was 0.5 millimeters. Now we use that same setting along with the distance from the laser to the surface of 1.606. The only thing that changed in between the two different trials with the two different lights is the wavelength of light passing through the contraption. So for the green light, we observed a fringe spacing of 1.7 millimeters. And again, with the red light, using the same settings, 0.04 millimeters slit width, 0.5 millimeters slit separation, and the 1.606 meters from the laser to the surface, the spacing between that was 2.1 millimeters. So doing a little bit of calculations, we took the known wavelength of the green and the red light. So in this case, the green light is 550 nm, and we plugged that into our equation with the other values that we calculated, and we received a calculated wavelength of 1.76 millimeters. So that is the expected fringe spacing for green light is 1.76. We observed 1.7 millimeters, with there being a 3.7% error in our work there. Moving to the red laser, we had an observed fringe spacing of 2.1. Using our known wavelength of 700 nm, we plugged that into our equation and we received a calculated fringe spacing of 2.24. And with our calculated fringe spacing being 2.24, we had a percent error of 6%. So a little bit more percent error on that one. But the entire project, the only thing we changed was the wavelength of light, and it increased the fringe spacing that much. So in conclusion, when using the equation and known wavelength for each beam, you can calculate the expected fringe spacing for each color of light. This also shows us that wavelength has a distinct effect on the way each beam behaves when passing through the machine.